Jai Hind students, today we are going to study about similar triangles. You have already studied about congruent triangles in your class 7 and class 9 also. Now what is the difference between congruent triangles and similar triangles? Let's learn about what is similarity. In geometry, two polygons are similar when one is replica of the other. That means the two polygons which look alike. So, consider Dr. Evil and Minnie from Mike Mayer's hit movie Austin Powers. So, Minnie is supposed to be an exact replica of Dr. Evil. So, they are similar to each other. Let's see these two figures. They are different in sizes but look alike. So, they are similar to each other. Now, these are few non-similar figures. In first figure, one is rectangle and one is a square. So, they do not look alike. Another, both the triangles, one is right triangle and another is acute triangle. So, they are non-similar figures. Now, let's see which triangle is out of A, B and C is similar to the first triangle. So, can you see and make out which triangle is similar? That is job for you. So, there is difference between similarity and congruency which we are going to study in this chapter. Before that, let's move to one theorem as basic proportionality theorem, which is also known as Thales theorem, as it was given by Thales. So, it says that if a line is drawn parallel to one side of the triangle to intersect the other two sides at distinct points, then the other two sides are divided in the same ratio. Students, as we know, we have a particular format or structure of the theorem. So, first point is given, which is triangle ABC where DE is parallel to BC, which you can see in the figure. So, figure is another format or the structure in the theorem. Then, what do we have to prove? When it's AD upon DB is equal to AE upon EC. So, we have a triangle ABC. DE is parallel to BC and we have to show that AD upon DB is equal to AE upon EC. That says DE is dividing both the sides in equal ratio. So for that we have to do some construction. We join B to E, C to D, then we draw two perpendiculars, DM perpendicular to AC and EN perpendicular to AB. Let's begin with the proof. Now you can see we take one triangle ADE and try to find out its area when we take base as ED. So our EN is perpendicular, AD is the base. So we have half base into height. So half AD into EN. Then we have area of triangle BDE, where we take BD as base. When we take BD as base, then angle at D vertex is obtuse angle triangle, whose perpendicular goes beyond the triangle and EN again is a perpendicular. So, half base into height, half into DB into EN. Then, we divide both the equations to get area of ADE is to area of BDE as half AD into EN upon half DB into EN. So, cancelling out the same factors in numerator and denominator, we get this as AD upon DB. Now, let's move to another part. We again take triangle ADE and now we calculate its area taking AE as the base. When we take AE as the base, we take DM as the perpendicular. So we have area of ADE as half AE into DM. Then we take triangle DEC, where this is again obtuse angle when we take EC as the base, and its perpendicular or height is again DM. So area of DEC becomes half of EC into DM. We again divide both equations 3 and 4 to get the ratio as half AE into DM, half AC upon DM. Again cancelling out the common factors in numerator and denominator, we get area of ADC is to area of DEC as AE upon AC. Now students, if you look at the equations A and B, left sides of both the equations, we see numerators of both the equations in left hand side are same, but denominators are different. But if we look at that area of BDE and area of DEC, these two triangles are made on the same base and between the same parallels DE and BC. And we have done in class 9 that 8 triangles on the same base and between the same parallels are equal in area. So a triangle BDE and DEC have same area. That means area of ADE upon area of BDE is equal to area of ADE upon area of DEC. So in our equations A and B, left hand sides are equal, so we can equate right hand sides also, and we get our required result AD upon DB is equal to AE upon EC. And this proves our theorem, basic proportionality theorem, which in short is also called as BPT. Let's look out for the converse of the BPT theorem. It says if a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. Again we move on to the structure of the theorem. We make the figure triangle ABC. There is a line DE which divides it such that AD upon DB is equal to AE upon EC. Now we have to prove that DE is parallel to BC. So what we do is we prove it by the contradiction, and we say we draw another line DE dash which is parallel to BC, but DE is not parallel to BC. Now when DE dash is parallel to BC, so by our basic proportionality theorem, AD upon DB is AE dash upon E dash C. This we are saying when we say DE dash is parallel to BC, and this has been given in both the equation. Our left hand sides are equal. When left hand sides are equal, we equate our right hand sides. So now we add 1 on both the sides. To get AC upon EC is equal to AC upon E dash C. Here we see that our numerators are equal on both the equations. So we have to say that our denominators are also equal. That says EC is equal to E dash C, which is only possible when E and E dash coincides. Because E and E dash coincides and we have considered DE dash parallel to BC, that says DE is parallel to BC, hence proves our theorem. Let's move to an example for BPT. Here we have been given two sides AD and DB as 1.5 and 3, 1 centimeter as AE. We have to calculate EC when DE is parallel to BC. So we have, by our basic proportionality theorem, AD upon DB is equal to AE upon EC. This has been given as 1.5, this is 3, this has been given, and EC has to be calculated. So when we look at our ratios, we get EC as 2 centimeter. Similarly, if we look at the second figure where we have to calculate AD, DB is being given 7.2, AE is being given 1.8 centimeter, EC is being given 5.4 centimeter. Putting all the values in the basic proportionality theorem, we get the value of AD. And we get AD as 2.4 centimeter. Now closely look at similar triangles. These are similar triangles that have same shape but not the same size. As I had discussed earlier also, the figures are look-alike. They are not of same size, they are only of same shape. That is the basic difference between congruency and similarity of triangles. In congruency, we have to have same shape and same size. But in similarity, we only have to have same shape, not same size. When we say triangles are similar, then they have several repercussions that come from it. We write triangle ABC is similar to triangle DEF only if angle A is equal to angle D, angle B is equal to angle E, angle C is equal to angle F, and the ratio of the corresponding sides are equal. We have AB upon DE is equal to BC upon EF and AC upon DF. So the ratio of all the three corresponding sides in both the triangles are equal. Now these are similar triangles if matching angles remains the same. So when two of the angles are same by angle sum property, third angle will also be same. So we have been given as these triangles to be similar. We have one angle in both the triangle as 50 degree, one as 120 degree and another as 10 degree. Rotation may be different, but when angles are same in both the triangles, that means triangles are similar. Then there are certain criteria like congruency and similarity also to prove that triangles are similar. One is AAA criteria, or we also say it as AA criteria. If in two triangles corresponding angles are equal, then their corresponding sides are in the same ratio or proportion, and hence the two triangles are similar. If I take triangle ABC and triangle DEF, where angle A is equal to angle D, angle B is equal to angle E and angle C is equal to angle F, then their sides will be in corresponding ratios and both the triangles will be similar, and we say triangle ABC is similar to triangle DEF. This is one criteria. Another criteria is SSS criteria, which says if in two triangles sides of one triangle are proportional or in the same ratio the sides of the other triangle, then their corresponding angles are equal and hence the two triangles are similar. Now in these two triangles we have been given that the sides are in the same ratio. We can say so angles are also equal and hence both the triangles are similar. Then we have SAS criteria, which says if one angle of triangle and the sides containing to it are in the same ratio to the angles and the sides containing of the other ratio, that says angle A is equal to angle D and AB upon DE is equal to AC upon DF. Then the two triangles are said to be similar. This is called as SAS criteria. So to prove similarity of the triangles we have three criteria: AA, SAS and SSS. Let's move to one example. Here we have to show that both the triangles are similar. We see that one side of the triangles are here AB of triangle is 3 cm, DE is 4.5. So 3 upon 4.5 is 6 upon 9 and 8 upon 12. All are equivalent to 2 by 3. So the sides of both the triangles are in the same ratio. So these two triangles are similar by SSS criteria. Now let's move to another theorem of the ratios of the areas of two similar triangles. The ratio of the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. Let's see its proof. We have two triangles which are already being given similar, ABC and PQR. Now as we have to consider the areas of the triangle, we do the construction as AM and PN, where AM is perpendicular to BC and PN is perpendicular to QR. We are only being given that triangle ABC is similar to PQR. We have to prove area of ABC is to area of PQR is AB upon PQ whole square is equal to BC upon QR whole square or AC upon PR whole square. Let's see how. We have already drawn perpendiculars to calculate the area. So area of triangle ABC, half base into height gives you half BC into AM, and area of PQR gives you half base into height as half QR into PN. Now when we divide both the equation, we get half BC into AM upon half QR into PN. That gives us ratio as BC into AM upon QR into PN. Let's see if we can replace this perpendicular or the altitude with some other side. Now if we consider triangle ABN and triangle PQN, these two triangles, here we have these two angles already equal because triangles are similar. This angle is 90 degree, so we can say angle triangle ABM is similar to triangle PQN, and we can say then that AB upon PQ is equal to AM upon PN, which can be replaced in our earlier equation A. When we replace AM upon PN by AB upon PQ, also BC upon QR is equal to AB upon PQ, because triangles are already being given similar. So we put all these in equation C to get area of ABC upon area of PQR as AB upon PQ into AB upon PQ, or the square of AB upon PQ. As we know, triangles are similar, their ratios are in correspondence. So all the area of ABC upon area of PQR is equal to AB upon PQ square, or BC upon QR square, or AC upon PR square, which proves our theorem. Let's take an example. We are being given triangle ABC and triangle DEF as their areas to be 64 centimeter square and 121 centimeter square. If EF is being given to be 15.4, we have to find BC. Now, as triangles are being given similar, so area of triangle ABC upon area of triangle DEF would be equal to BC upon EF square. That says 64 upon 121 is equal to BC upon 15.4 square. Taking square root on both the sides, we get 8 upon 11 is equal to BC upon 15.4, and BC as 8 in 15.4 upon 11, which gives us 11.2 centimeter. Let's move to another theorem for Pythagoras theorem. But before proving Pythagoras theorem, we have to look at another theorem which says if a perpendicular is drawn from the vertex of right angle of a right triangle to the hypotenuse, then right triangle on both the sides of perpendicular are similar to the whole triangle. Let's see the figure. So this is the figure. A, B, C, where B is 90 degree. If we draw the perpendicular BD, it says the triangle on both the sides of BD are similar to each other and to the whole triangle. This theorem will be used to prove Pythagoras theorem, which says if a right triangle, the square of hypotenuse is equal to the sum of the square of other two sides. So what is being given to us? A right triangle, right angle at B. What is to be proved? AC square is equal to AB square plus BC square. What we have done the construction is, we have drawn perpendicular BD on AC. Now since this is perpendicular to AC, that says triangle ABD is similar to triangle ABC, and also triangle BDC similar to the big triangle ABC. Using this, ADB is similar to ABC, so sides will also be in proportion. AD upon DB. AD upon AB would be equal to AB upon AC. So smaller triangle this side and the bigger triangle this side, hypotenuse of the smaller triangle and the hypotenuse of the bigger triangle, that gives us AD into AC as AB square. Similarly, we take triangle BDC and the bigger triangle, as they are similar, we say CD, this side of the triangle, upon BC, and then hypotenuse of this triangle to the hypotenuse, which says CD into AC is equal to BC square. When we add both the equations, we get AC AD plus CD into AC as AB square plus BC square, and we can see AD plus CD is AC, so AC square is equal to AB square plus BC square, and which proves our Pythagoras theorem. Let's look at converse of Pythagoras theorem. Now in a right triangle, the square is of one side is equal to the sum of the square of other two sides. Then we say the angle opposite to first side is right triangle. Let us take triangle ABC. Now here no angle is being given right triangle, but we are being given AC square is equal to AB square plus BC square. We try to construct another triangle in which the side PQ is equal to AB and QR is equal to BC, but this is right triangle. So when this is right triangle, we can say that angle Q is 90. So by Pythagoras theorem, PR square is equal to PQ square plus QR square. Now PQ is equal to AB, QR is equal to BC. Replacing PQ and QR by AB and BC, we get PR square is equal to AB square plus BC square. Now we already know AB square plus BC square is also equal to AC square. That says PR square is equal to PR square is equal to AC square, or PR is equal to AC. Now we have shown that all the three sides of both the triangles are equal. So hence by congruency SSS, we can say that triangles are congruent, and when triangles are congruent, their angles are also equal by CPCT. Hence angle B is equal to angle Q. And angle Q we have already considered 90. So angle B is also 90, and this proves our converse of Pythagoras theorem. Let's look at an example on Pythagoras theorem. We say a ladder is placed against the wall such that its foot is at a distance of 2.5 centimeter. So we can consider this as the ladder. The distance is 2.5. It reaches a window of 6 meters. You have to calculate the length of the ladder, which can be considered as L. Now it frames a right angle triangle. So we can say AC square is equal to AB square plus BC square. That says 6 square plus 2.5 square. So 6 square is 36 plus 6.25. That gives us 42.25. So AC comes out to be 6.5 centimeter. So length of the ladder is 6.5 centimeter. Hence this gives an idea of Pythagoras theorem. We can look at our concept map of similar triangles. There is similarity of triangles. There is basic proportionality theorem. Similarity can be proved through three criterion: SSS, SAS and AA criteria. Then we have Pythagoras theorem and converse of Pythagoras theorem. Thank you, students.